Good afternoon. Today we continue our course Applied Geomechanics for Geologists, and we will consider horizontal stresses. This is lecture plan for today, and first topic of lecture plan is applied horizontal stresses. Applied horizontal stresses consists from prediction of borehole stability, optimization of well trajectory, safe mud window, hydraulic fracturing design, finding out of out-of-zone injection, and maximum operational injection pressures. Also, it allows find out most optimal angle of horizontal drilling and multiple fracturing. The next topic is basic definition. And in simple terms, stress is force divided by any area. Okay, it's important to note that stress is actually a tensor, which means it describes the distribution of all forces on subsurfaces passing through a specific point. In the context of continuum mechanics, the stresses on homogeneous and isotropic medium can be described by a second-rank tensor with 9 components. To fully describe the stress state at depth, one must define either S6 stress magnitudes or 3 stress magnitudes and 3 angles that determined their orientation of stress coordinate system in relation to a reference coordinate system such as geographical coordinate system or well-bore coordinate system and another coordinate system. Once the stress tensor is determined in the one coordinate system, it can be used to calculate stress in any coordinate system through tensor transformation. To perform this transformation, we must define the direction cosines. S, A, and G is shown medium figure that represents the rotation of the coordinate axis from the original to the new coordinate system. Tensor transformation is essential for representing stress state at various depths in terms of principal stress. These 3 principal stress operate the principal coordinate system, simplifying the description of stress state its original position. The principal coordinate system is where shear stress vanish R0, defined by 3 principal stresses S1, S2, and S3, which completely define the stress field. This idea is illustrated on the accompanying figure at the right of the slide. By diagonalizing the stress tensor in the principal coordinate system, the principal stresses corresponded to the eigenvalues of stress tensor, and the principal stress direction corresponded to its eigenvalues. This is the one set of axes with respect to which all shear stress are 0, and 3 normal stress have their extreme values as shown in figure. These 3 perpendicular planes are called principal planes. Consequently, 3 normal stress acting to their planes are principal stress. It's very convenient for specify the stress state because they provide direct information of maximum and minimum values of the normal stress components. The value S1, S2, and S3 in figure are principal stress, and S1 more than S2 and S2 more than S3. The effect of pore pressure on the mechanical properties of saturated rocks has been investigated by Terzaghi in his work. He proposed the concept of effective stress of Terzaghi. On this case, you can see the representation of coefficient BO. This is BO at pore elastic coefficients. This is includes in effective stress formula, where sigma x, this is effective stress, Sx full stress, absolute stress, and pp, this is pore pressure. Okay, the next topic is stress regime. In situ stresses are most important parameters for geomechanical modeling. Generally, in situ stresses include three orthogonal principal stress in the subsurface, as I considered before, considered before, which can be defined as the vertical stress and maximum and minimum horizontal stresses. The three in situ stresses correspond to three principal stress, namely the maximum principal stress, intermediate principal stress, and the least principal stress. Okay, according to the relationship of these three principal stress, free in situ stress regime can be used to describe in situ stress state based on the faulting theory. This is three stress regime: normal fault, strike slip, and reverse fault. Assuming that there are critically oriented faults constraining stress magnitude, the more column criterion expressed in the principal effective stress form for a fault if there are no any shear failures. This is more column criterion expressed in this slide. Okay, for deep layers, the fault cohesion can be neglected and can be simplified. Therefore, to avoid a fault from friction sliding, the in situ stress should satisfy the following equation, whereas sigma 1, this is effective stress, and S1, this is absolute stress. Okay. So, substituting the total principal stress into upper equation, there is in situ stress can be expressed in the following equation for different faulting stress regime. The first faulting regime, this is normal fault, whereas vertical stress is maximum principal stress, and SHmin is least principal stress. Second stress regime is strike slip, whereas as maximum principal stress is SHmax, as vertical is intermediate principal stress. And finally, this is a reverse fault, whereas SHmin and SHmax, this is intermediate principal stress and maximum principal stress. The drilling-induced tensile fractures can be also horizontal in vertical well. In the reverse faulting stress regime, hydraulic fractures are open or closing against the vertical stress because the axial stress in the borehole axial direction induces the tensile fractures. The next topic is stress polygons. A stress polygon at given depths can be drawn using the relationship of in situ stresses and stress and pore pressure in different stress regime from above equation. We'll consider the example of stress polygon. The input data are presented in the right table and the stress expressed in gradients. The point number 1 is overburden. Okay. Point number 2 is the upper limit of SHmax. We can calculate it from frictional limit equation for the normal regime. I spoke about it before. And finally, the point number 3 is the lower limit of SHmin. We can find it from frictional limit equation for normal regime. Okay? After we close this point, and after it, we divided the closing polygons on 3 parts and get 3 area, whereas upper area is reverse fault, strike slip, and normal fault. Okay? The stress polygon has been used for decades to constrain in situ stress. Based on Byerly law, it's assumed the coefficient of friction of the fault it's a constant across the entire fault plane, whereas mu from 0.6 to 0.7. Nevertheless, many researchers concluded that the minimum horizontal stress can be calculated from mu equal 0.6. Underestimate the minimum stress doesn't match the measured data. For example, any researchers concluded that all faults in the vicinity of transform plate boundary of the Western Union, USA are frictionally weak to very weak. Whereas mu equal near 0.2. On the figure, there is a comparison of three stress polygon. The stress polygon with mu equal 1 bigger than mu equal 0.6. The stress polygon with pore pressure gradient 1.6 less than pore pressure gradient 1.3 and 1. Because increasing of pore pressure according earlier considered formula leads to decrease boundaries of stress polygon. In this case, considered overburden gradient and its influence or sizes of stress polygon. Combined stress polygon where combined the previous results. Okay, let's continue and go to the horizontal stress orientation. The orientation of maximum horizontal stress is a crucially important parameter for designing hydraulic fracturing and optimizing drilling direction. For a vertical or near vertical borehole, the maximum horizontal stress orientation is aligned to the direction of tensile drilling-induced fractures and perpendicular to direction of borehole breakouts. The borehole image log can be also used to identify borehole breakouts. Figure displays a section of ultrasonic borehole imager log data processing to the one of vertical well. SHmin azimuth is 90 degrees according breakouts orientation. Consequently, SHmax direction is near 0 degrees. Okay? This is breakouts and tensile drilling-induced fracture. This is picture characterized breakouts, and this is picture characterized tensile fractures. Okay? This is examples of tensile fracture before stress test and after stress test. You can see on the picture on this slide, on picture number A, there is no any tensile fractures before stress test and after stress test. You can see at the same picture a vertical tensile drilling-induced fracture. This is another picture that and you can see here natural fracture and drilling-induced fracture. At a natural fracture, a microimager picture very many random fractures. As for drilling-induced fracture, this is usually one and a couple of drilling-induced fracture that usually are vertical. Acoustic stress-induced anisotropy and stress direction are important inputs for geomechanical studies. In an anisotropical formation, the shear splits into perpendicular component, a fast shear and a slow shear. The fast shear azimuth may correspond to the maximum horizontal stress direction, and low shear azimuth may correspond to the minimum horizontal stress direction. Let's compare stereo nets. Black filled triangles on the stereo nets mean direction of tensile fractures, and red triangles correspond to the SHmin direction and breakout. Estimated value of SHmax azimuth is near 150 degrees in all three cases. The world stress map is a global compilation of information in the crustal present-day stress. It's a collaborative project between the academia and industry that aims to characterize the crustal stress pattern and to understand the stress sources. All stresses information is analyzed and compiled in standard format and quality ranked for reliability and comparability on a global scale. World Stress Map is an open access public database. The next topic of lecture plan, horizontal stresses magnitude. Methods for determination or in situ rock stress can be classified into two main categories. The first consists of methods that disturbs the in situ rock condition by inducing strains, deformation, or fracture open. The following methods may be included in this category: hydraulic methods, including hydraulic fracturing and hydraulic tests on pre-existing fractures, borehole relief method and surface relief method. The second consists of methods based on observation of rock behavior, without any major influence on from the measuring method. The following method belong this category: statistic of measured data, chord descent, borehole breakouts, relief of large rock volumes, acoustic methods, also a Kaiser effect, strain recovery method, and another method. The method also may be classified by the operational type, as indicated of the rock volume involved in their use provided, and it's shown in a table on this slide. This is a common table of stress measuring method that I spoke about before. So the minimum horizontal stress can be determined by direct measurements as hydraulic fracturing or its field equivalent extended leak-off test. In a hydraulic fracture test, an interval of borehole is isolated and sealed with puckers. In a typical LOT, XLOT, it's a simpler that one presented in figure. Because the casing in the borehole seals the shallower formation. Therefore, only the hole below the casing and any new formation drilled before the test are exposed. The fluid is then pumped into the hole with a constant flow rate. Okay, this is point FIP, formation integrity pressure and leak-off pressure. The pressure increased in the hole is typically linear as long as there are no leaks in system. As the pressure increased at some point, the rate of pressure increased, whereas side that the pressure curve time departs from linearity. This departure from linearity is the leak-off test. After departure from linearity, pressure is typically seen to increase at a lower until the maximum pressure is reached, and this pressure is called as formation breakdown pressure. Okay. After the rock is broken, at some point the pressure in the hole levels off and remain fairly constant. During this stage, the fracture propagation pressure. When the pump is turned off, the pressure begins to decline and the pressure drops to instantaneous shutting pressure, ISIP. Okay. As the pressure declines, the fractures start to close. Therefore, the minimum principal stress is equal to the closure pressure, the inflection point in the pressure decline curve. Okay, this is finish of cycle number 1, and after this we consider cycle number 2. Okay, if you note that after cycle number 2, you don't see any more fracture breakdown pressure because the fracture has already been after cycle number 1. We observed only repeat fracture propagation pressure, instantaneous shutting pressure, and fracture closure pressure. As you note, fracture closure pressure in cycle number 1 and cycle number 2 equal. There is equal by definition as S3. Okay. There is typical example of XLOT interpretation in field condition. There is a leak-off point. Leak-off test is a pressure and flow test conducted on a well-bore casing. It's necessary to determine its minimum pressure capacity of integrity. It involves pumping drill fluid into the casing and gradually increasing the pressure until it leaks from the subsurface, indicating that the casing integrity has been exceeded. Formation integrity test FIT. This is the method to test strength of formation and ensure by increasing bottom hole pressure to design pressure. FIT is normally conducted to ensure that formation below a casing shoe will not be broken while drilling the next section with higher BHP of circulated gas and fluids in a well-controlled situation. Normally, drilling engineers will design how much formation integrity test pressure required for each hole section. Okay, this is a comparison table of XLOT, load, and FIT. It's let's note that the most interesting in terms of calibration of geomechanical model is XLOT test, because he defines fracture closure pressure that by definition equal S3. Another tests define formation integrity pressure and leak-off pressure that that can be can be also used for calibration of geomechanical model, but it's not pricely. It's not absolutely. Okay, this is empirical equation table for SHmin. There are near most well-known methods for definition of SHmin. Also, it can be observed in the figure that sandstones normally has a smaller minimum horizontal stress because it's smaller Poisson's ratio. By contrast, a shale gas a higher minimum horizontal stress. Therefore, the shale can be used as a barrier of hydraulic propagation, hydraulic fracture propagation when hydraulic fracturing is performed in the adjacent sandstone. This figure presents measured minimum horizontal stress profile with depths. The minimum horizontal stress in the mudstone at any given depth is considerably greater than that in the sandstone. This might be caused by the sandstone, which have a lower Poisson's ratio than in the shale, or by lithology-dependent phenomena. Let's consider next topic, stress pass effect. Edis and Zhang analyzed the stress depletion response in several petroleum reservoir. The depletion induces a stress pass is very different in different fields. The table lists measured stress pass in some petroleum basins. Data from hydrocarbon basins document the systematic relationship where pore pressure depletion from oil and gas extraction in both conventional and unconventional reservoir is associated with a reduction of the minimum and maximum horizontal stresses. This figure presented a pore pressure and in-situ stress profile before and after depletion in the sand oil reservoir as an equivalent depth of 2 kilometers. Okay, this is original SHmin and changed is SHmin after depletion. Okay, it's shown the depletion in the pore pressure greatly reduce the minimum horizontal stress. Measurement from the diagnostic fracture injection test, the feet in the middle bucket and free forks place shows that the minimum horizontal stress decreases linearly with reservoir pressure. By analyzing the instantaneous shut-in pressure ICP in a tight, low porosity, low permeability sandstone in Swissburg formation, obtained that the following linear relationship between the minimum horizontal stress and the pore pressure. Westcom data, field data show that stress pass coefficient as high as 1 is not abnormal in the initial stage of depletion. This phenomenon has been observed where a long-term database of frag gradient is maintained. Stress pass coefficients usually reduce to values lower than 1 over time, but in a non-linear manner. Okay, this includes some trends. The most trend where is stress pass effect near 1 and reduce to 107, 108. When the measured data are not available, the depletion-induced minimum stress reduction may be estimated based on the assumptions of minimum horizontal stress in axial strain boundary condition in the following equation. Typically, the total horizontal stress in reservoir changed by between 0.4, 0.7 compared the pore pressure change. The Morse circle plots are useful to representation the depletion effect on the reservoir rock and for demonstrating how stress changes in the reservoir during its production history. As described in the previous section, the minimum horizontal stress decreases as the reservoir depletion increases. However, the vertical stress doesn't change much. Therefore, vertical effective stress increases as the depletion increases. Thus, a large stress difference in the effective vertical and minimum effective horizontal stresses is decreased as depletion increases, and the Morse circle becomes larger. Figure presents the Morse circle and the relationship of the minimum effective horizontal stress, effective vertical stress, shear stress, and the failure envelope for different degrees or depletion. If the Morse circle touches the Moore column criteria, then slip on optimally oriented fractures will occur. The smallest Moore circle in figure represent the initial effective stress start before. The largest Moore column circle has a pore pressure after 3000 psi of depletion. In either case, shown in figure, the Moore circle grows and approached critical stress with a continued depletion. Okay. Figure is a Moore column circle illustrating the mechanism of shear failure induced by repressurization. The rapid pore pressure increase doesn't diffuse significantly into the matrix, and the injection doesn't change the total stresses, but simply reduces the effective stresses, moving the Moore circle to the left. According to figure, depletion causes a decrease in a reservoir total horizontal stress in addition to pore pressure. The total stress change that accompanies the pore pressure change is known as the stress arching. When the stress arching is generated due to reservoir depletion, partial amount of total stress is supported by overburden and underburden formations. The total stress change induced by fluid production or injection stress arching can have negative consequences such as cap rock failure, fault reactivation, wellbore, and casing damage. Step number 1, this is initial stresses. This is we observe changing stresses due to injection and depletion. Okay. Yeah, please note that after injection in reservoir, the minimum horizontal stress also increases, but in adjacent rocks, adjacent seal, we observed decrease of SHmin, that it can be lead to normal faults in seal and reverse fault activization in reservoir. Another case we see in depletion case. and in depletion case in reservoir SHmin decreases, and in the seal SHmin increases. Okay, let's go to the practical cases. Fracture closure pressure was used for the estimate calibration of SHmin magnitude in reservoir, and closure pressure gradients in this case is 1.7 and 1.73 gram for cubic centimeter. Please note this chart. This is typical XLOT that we discussed before. And red point is fracture breakdown pressure, PBP. This is ISIP and fracture closure pressure. In this case, the fracture closure pressure calibrated on SHmin profile. ISIP, instantaneous shut-in pressure, calibrated on SHmin in the seal. This is reservoir, this is seal. And fracture breakdown gradient calibrated on the fracture breakdown pressure. This is good work of one of researchers, Ferlaza. He shows us that he can calibrate results of microfrac tests and calibrate this 1D geomechanical model and uses it for calibrate of maximum horizontal stress and definition from minimum and maximum horizontal stress breakdown profile. This is great work of one of my colleagues from Tumin. He shows that the very much risks after increasing equivalent circulated density above profile of SHmin. Okay, this is one of the works of Jung. He also shows then after increasing KCD more than SHmin, there is very much losses incidence that a very bad drilling event, and it can be avoided if you will use ACD less than SHmin. Okay, this is one of the example of ACD equal SHmin. After this, there are observed big amount of. This is one of example where it was studied reservoir and seal between two reservoir. The seal has carbonatite mineral composition, and if you can see here, the minimum horizontal stress in seal more than minimum horizontal stress is to reservoir. Okay. By this link, you can go to the horizontal stresses calculation in LithoStudio software by QR code or link. This is reference used for prepare of this presentation. So this presentation made with Slides Go templates. Thank you, Slides Go.